This is the first in a series of videos that members of TENNLab will be making to go over neuromorphic computing and the research that TENNLab is doing with neuromorphic computing. This is the first video. I'm Jim Plank, and this is going to be just an introduction to neuromorphic computing and an overview of TENNLab. As an aside, I re-record some of these slides from time to time just to keep them current, so I apologize if it's jaggedy in nature. We have 4 PIs of TENNLab, all professors at the University of Tennessee. Each one of us is responsible for a different part of TENNLab's mission. And we have received continuous funding for coming on 7 years, the majority of it coming from the Air Force Research Lab and the Department of Energy. We have been around since 2014, and we have had a variety of students, undergraduates, graduates, and postdocs who have done research with us and have been responsible for a lot of the research results that I will show you in this sequence of videos. The research mission of our group is to explore brain-based or neuromorphic computing, and we do this at all levels. We work from materials to circuits, to electronics, to systems, to software, to simulation, and machine learning. We're a large group, and we kind of attack all parts of neuromorphic computing. We are making these videos to just give you an idea of what it is we do. We'll introduce you to neuromorphic computing, what it is in general, kind of give you an overview of what research we do, and then to show you that neuromorphic computing is machine learning beyond simple classification, which is a common misconception that people have when they see machine learning and neural networks. We're also going to introduce you to our software framework, which is large and we hope flexible enough to encompass a lot of research needs. And then we're going to also help you use our software. In fact, a large portion of these videos is just to get you started so that you can use our software and hopefully help it aid you in whatever research you want to do. We'll start off with the basics. Neuromorphic computing is all about spiking neural networks. And spiking neural networks are composed of 2 components, neurons and synapses. Neurons you can view as nodes on a graph. Each one holds a value which is called its potential. It might hold more things, but each one always has a potential. And each synapse is like an edge on a graph, and a synapse communicates a temporal spike event from a pre-neuron to a post-neuron. So there's the spike that comes out of the pre-neuron, and then it travels in time along the synapse until it arrives at the post-neuron. Synapses always have 2 parameters. First is delay, which is how long it takes in time, maybe simulated time, to the spike to go from the pre-neuron to the post-neuron. And a wait is how much value does the spike add to the action potential of the post-neuron when it arrives. So for example, we have a synapse here with a delay of 2 and a wait of 0.5, and the spike travels. It takes 2 units of time to get from its pre-neuron to the post-neuron, and when it arrives at the post-neuron, it adds its weight to the action potential, which went from 0.3 to 0.8. Now, neurons also have a parameter called threshold, which is typically settable, and when its potential either achieves or exceeds the threshold, then the neuron fires, which will send spikes along all of its outgoing synapses, and then it'll reset the potential to a resting value, which is typically 0. So an example here, we have the same synapse coming into the same neuron, and we have another spike coming in with a weight of 0.5. When it arrives, the potential goes to 1.3, which exceeds the threshold of 1, and so the neuron fires, and spikes go out of its post-synapses. Now, computing with spiking neural networks is a little bit of a mouthful. It's a four-step process where first you define the neural network, which means you define the neurons and the synapses, how they're connected, what the thresholds of the neurons are, and what the weights and delays of the synapses are. Then, given your problem is going to have values that will be input to the neural network. Those need to be converted into spikes, and then they are applied to special neurons called input neurons. Then the neural network runs temporally because it's spiking. And then at certain neurons, which are known as output neurons, we record the spiking events, and then we're going to convert those spiking events into values. And this is how the networks compute. Now I'll give you a really simple example. This is a three-neuron neural network, which computes a binary OR operation. And so I have all the parameter settings there in the picture. All the neurons have thresholds of 1. The two synapses have weights of 1 and delays of 1. And what this does is calculates a binary OR. So next, what we do is we have to convert our input values into spikes. So the way we're going to do that is if our input value is 0, we're not going to have any spikes. If our input is 1, then we're going to apply a spike to the appropriate input neuron at time 0. And let me give you the example. Here's the first scenario. If our two inputs both equal 0, then there are no spikes, and the system doesn't spike. And that's a way of saying that 0 or 0 equals 0 because there's no spiking. In the second scenario, the value A is 0, but the value B is 1. So we apply a spike to B at time 0, and then it travels during its time unit, and at time 1, it arrives at the output neuron, which has a threshold of 1, so it fires. So the output neuron fires at time 1. Now we have a third scenario. That's when A is 1 and B is 0, and this does the exact same thing as the previous scenario, except it's A that's making it fire instead of B. And then in the final scenario, both A and B equals 1, so they both fire at time 1, and so their spikes arrive at the output neuron at the same time. It'll add up the weights, which will equal 2, which again exceeds the threshold, so the neuron fires at time 1. So these networks compute by applying your inputs at time 0 and then looking at the output neuron at time 1. If it spikes, then A or B is true. If it doesn't, A or B was false. Now let me give you a more complex example. This is a neural network that we trained with machine learning, and what we have is the cart pole application. This is a control application where we have a simulated cart with a pole on it, and the pole can fall down to the left or the right, and you are allowed to push the cart left or right, and your goal is to keep the pole up. Now, the way we communicate input to the neural network is we have 4 different input values, which is the cart's x position and its x velocity, and the pole's angular position and its angular velocity. Those are given as inputs to the neural network. They are converted into spikes, and then the neural network computes, and then there are 2 output neurons, and at periodic intervals, this is a 50th of a second simulated, you count the number of spikes on each of the output neurons, and if the one corresponds to pushing left, one corresponds to pushing right, and whichever one spikes more, that's the appropriate action. And this process repeats itself every 50th of a second, and the neural network has been trained to keep the pole upright or not fallen over, and to keep the cart in the middle, not hitting either end of this simulated environment. So we can see it going here. So this is an animation of the neural network keeping the pole up. As you can see, as the pole shifts position and angular position, the different input neurons, which are the top 8, each one of those inputs is split into 2 neurons, or different ones fire, and then different activities cause the cart to go left or right. And as you can see, the neural network is keeping the pole upright. So neural networks can be enriched with a lot of things, and I have written here a bunch of them. Plasticity, meaning that that synapse weights can change according to whether or not they cause neurons to fire. Leak means the action potential will settle down to a base value over time if nothing happens to the neuron. Stochasticity is when neurons have varying random behavior and aren't deterministic. There are different accumulation models where you can simply add, or you can have some calculus-based function on how you accumulate input, et cetera, et cetera, et cetera. Now, just as a concluding slide, As I said previously, in TENNLab, we work on every single part of this research system, from building spiking neuroprocessors out of electronic and sometimes non-electronic material, to developing the circuit model and the electronics behind building a spiking neuroprocessor, to simulation and applications, to machine learning and training, and other algorithms for working on neuromorphic computing. Now, what we're going to have on our website is a series of videos which will walk you through some research and, in particular, some software. The idea being that if you want to join up with us, we will give you access to our software repository and then help walk you through using our software so that you can then do research with it in whichever part of neuromorphic computing you wish to address. Thank you.